So hello everyone. What we're going to do today, since I wanted to go over the homeworks, but the homeworks they have been answered on a Blackboard by Ricardo, so there's no need for me to go over the homeworks. What I'm going to do, we started this exam, so this is from 2015 midterm exam 2. We went over some of the questions, not all. We're going to go over the rest of the questions, and then if we have more time, we will go over the exam for 2014. So if there's no question, we can start. So the question 2, we didn't answer the class, and I can answer it right here. Okay, draw. Yes, so question 2. Is the first one we're going to answer. So, are two subpopulations the same size? One has a allele frequency p of 0.1 and the other one 0.7 at a locus with two alleles, assuming that both subpopulations are in Hardy-Weinberg equilibrium, have the same size. What is the heterozygosity of the global population formed by pooling the two subpopulations? So first of all, the idea they are referring to is called the Volund effect, which is the effect of subpopulation on Hardy-Weinberg, or the way we perceive Hardy-Weinberg if a population is actually subdivided into subpopulations. In this case, we don't need to, or we don't want to see what we would expect given the population structure, but what would be the observed heterozygosity. So for the first population, so let's call P1, which is 0.1, the expected heterozygosity, or because these are in Hardy-Weinberg equilibrium, both of them. So for the first one, heterozygosity would be 2pq, which is 2 multiplied by 0.1 multiplied by 0.9, which would be, what is it, 0.18? Right, so that's for the first population. For the second population, let's call that P2, which was 0.7. Heterozygosity would be 2 multiplied by 0.7 multiplied by 0.3, which is 0.42. So now we know the heterozygosity expected, and well, that should be the actual heterozygosity we observe, given that both populations are in Hardy-Weinberg equilibrium. So now the question is, what should we do with these two values? So we have two heterozygosities. What we're going to do is to calculate the average, so we're pooling the two subpopulations. So we simply add the two. 42 plus 0.18 and divided by 2, which would be 0.3. Oh, that is a bit. Oh, let's move it. Okay. So 0.3 is the right answer to this question. So was it clear? Any confusion regarding this? So again, to recap, we didn't want to calculate the expected heterozygosity. We simply wanted to calculate the observed heterozygosity, which would be the average of heterozygosities in the two subpopulations. And since both subpopulations are in Hardy-Weinberg equilibrium. You simply calculate the expected Hardy-Weinberg heterozygosity and then average those values. In this case, we only had 2 subpopulations, so the average of these 2 would give us the right answer. Moving on, so we went over these ones. What is that? Oh, this is a very poorly made software. Okay, I think we went over all the questions until 10. Okay, now here. Question 11. So, again, the rest of the questions thus far we covered in the class, except for the second question. Actually, oh, there was a question 7, actually. Okay, which we didn't. So, question 7 first. So question 7, consider the following populations with different numbers of reproductively mature individuals in 3 consecutive generations. Which population has the largest effective population size? From the lectures, you remember that, so in the case of population or changing population size, so these so-called bottlenecks, using a simple mean is not enough, because the way we calculate mean usually is not sensitive enough to small values or smaller values. So we ended up using something called a harmonic mean, which in this case would mean that the effective population size would be, so the number of generations denoted by t divided by 1 over n1 plus until 1 over nt. So the population size at time in the first generation. What happened? That was very interesting. Okay. So 1 over. I'm not sure what was that. There's a spooky moment there. So 1 over n1. So population size. Why is that interesting? I'm not sure. Anyhow, so the harmonic mean is what we're going to use. So I'm going to calculate for all of these. I've actually written a program which would do that. So I'm just going to use that, since it would take a while to calculate. So for the first population, it's 50, 100, and 90, which would be 73. So for the first one is 73. Okay, for the second one is 100, 19, and 80. 90 and 80, which is 89. For the third one, it's 90, 60, and 200, which is 92. For D, it's 400, 40, and 90. 40, 400. This 78. And for the last one, it was 800, 20, and 90, which is 48. All right, so as you can see, so the highest one is the third one, okay, this one, with a population size, effective population size of 92. It's worth noting that, so in the case of D and E, even though at some point they have pretty big population sizes. In the case of D, you go up to 400. In the case of E, it's a staggering 800, which in comparison dwarfs the rest of values in these options, even though they at some stage they've had some of the bigger populations. The actual population size, the effective population size, is highly reduced. In the case of D, mainly because of the 40. In the case of E, the size 20 greatly reduces the effective population size. So it can be confusing or deceptive for you to just look at the numbers. As you can see, you have to calculate them to. It's not simply looking at the numbers to see which one has the biggest population size, because we are concerned about the overall trajectory. All right. Question 11. Okay. Again, the rest of the questions were covered. Questions were covered in the class on Thursday. So 11. The following figure shows a measure of genetic variation in 17 island populations of the Galapagos lava lizard. So on the y-axis, we have the mean number of alleles. So that could be heterozygosity for you. It doesn't really matter. So genetic variation, and on the x-axis, it doesn't matter if it's logarithmic. It's just the island area, so the size of the island. So how do you interpret these results? A, smaller islands contain larger populations, which causes genetic drift to act less strongly, which in turn causes a reduction in genetic variation. So first of all, does anyone know what was the relationship between drift and heterozygosity? So what is the relationship between genetic drift and heterozygosity? Does drift increase heterozygosity or decrease it? Anyone? So what is the relationship between drift and heterozygosity? Does anyone remember? Okay, let's no one really. Okay, let's put it. So from the different heterozygosity or different experimental results, we know that heterozygosity declines less in bigger populations, and as populations become smaller, the decline in heterozygosity over time. So as we go down, it's smaller population. So on the y-axis here, what I drew is heterozygosity. Here on the x-axis is time. So this trajectory is a largest population here. The middle one is a mid-size, and the lower one is the smallest population. As you can see, as population size decreases, heterozygosity reduces as well. And as we know, the strength of drift is proportional to population size. So the relationship should be an inverse relationship, right? So in A, it says the smaller islands contain larger populations. First of all, from this, we can't really assume that. So it causes genetic drift to act less strongly. So large population would result in drift to act less strongly. So that part is true, which in turn causes reduction in genetic variations, which is also logical. So except for the first part, when it says smaller islands contain larger populations, the rest is logically sound. B, smaller islands contain large populations. which causes a natural selection to act more strongly, which in turn causes an increase in genetic variation. Smaller islands contain the smaller populations, which cause genetic to act less strongly. So again, here in C, smaller populations means more drift, so this one is wrong. D, smaller island contains a smaller population, which causes genetic to act more strongly, which in turn causes reduction in genetic variation. A smaller island contains smaller populations, which cause genetic selection to act more strongly. So E is wrong as well. So we are now between A, B, and D. So again, just go over them again. So in D, smaller islands contain smaller populations. So the area, okay, so area and mean heterozygosity, they have a positive relationship, right? So as the island gets bigger, so on the graph, so here, as you move from here to here, so from down left to up right of the graph, the heterozygosity increases as island size increases. So smaller islands should have lower heterozygosity. So which one? So in the A and B, we have a small island with large populations, so that can't be the case because large population would mean a lower heterozygosity. D says small islands contain small populations, which is causes genetic drift to act more strongly, so smaller populations, more drift, which in turn causes a reduction in genetic variation. So D is the correct answer. So any question about this, about question 11? If not, we can move on to, okay. Question 12. Actually, there's several people typing, so there's no question. Okay, question 12. How long is a neutral allele that has just arisen by mutation in a population of 500 diploid individuals expected to take to reach fixation? So this one actually is from the Kimura's equation. We know that it's 1 over 2n for a neutral allele to go to fixation. So that's the probability. 500 diploid individuals, so 500 is 2n here. So 500 is our 2n, so it should be 1 over 500. So it should take 500. Also, how long does it take? Also, they don't want the probability; they want the time. So this one is the probability. So let's. So the probability that an allele. So the probability of fixation is 1 over 2n for a neutral allele, and the time, the average time to fixation is 4n for a neutral allele. So in this case, it should be, so we have 2n, so n would be okay, so how long is neutral allele that has just arisen take to reach fixation? So it should be 2. That can't be. 500 diploid individuals. 1 allele. Is it 1 of, so it's 4? It is 4n, right? Is it not? 500 individuals that are diploid. Okay, so it should be 2,000 then. So 2,000 seems to be. So it's 500 individuals. They are diploid. So it's 5. So each one carries 2 copies. So there are actually 1,000 haplotypes. So that would be 2n is 1,000, 4n would be 2,000. 13. A population is genotype at 100 loci. Several of these loci show multiple alleles at intermediate frequencies. How would the hypothesis of neutralism explain this observation? Just to remind you, there was the idea of neutralism versus selectionism. And neutralism, the idea that most mutations are neutral. Selectionism would be that most mutations are selected for. So there's the idea of drift working, working on and shaping the allele frequency over time versus selectionism. So which one would be? But the problem is, how would you explain the intermediate frequencies of some loci, given the neutralist view, which would assume that that frequencies are changing according to genetic drift and not selection? Alleles are maintained by directional selection. That can't be the case because neutralism is not about selection. The alleles are maintained by heterozygote advantage or negative frequency dependent selection. The alleles are maintained by heterozygote disadvantage or positive frequency dependent. The alleles are transient because of selection. No. So E would be the case, right? So it's like we are looking at the changes according to genetic drift. Again, neutralism is the idea that it's purely drift, or mainly drift, shapes the trajectory of evolution. Question 14. Thomas and colleagues used human and rodent sequences to estimate the rates of nucleotide substitution of 121 genes involved in cancer in humans. They found that the rate of nucleotide substitution per non-synonymous site was DN 0.05, and the rate of nucleotide substitution per synonymous site was 0.64 on average. Why is DAN lower than DAS in these genes? So there's the idea of, I think you probably remember, or you should, is the DN to DS, the rate of change of non-synonymous substitutions. So substitutions that would make difference, right? So substitutions that have, so in the case of non-synonymous ones, these ones would have effects on fitness potentially. And in the case of DAS, these are synonymous substitutions, so they should have no effect whatsoever. And the assumption was that when DAN, DS, the proportion is bigger than 1, most alleles are beneficial. If it's smaller than 1, most alleles or most substitutions are deleterious. If it's equal to 1, most substitutions are neutral. So in this case, DN is much lower than DS. So A, is it because a large proportion of mutations in non-synonymous substitutions are beneficial when compared to mutations? So that would result in a DNDS that is bigger than 1. In this case, it's lower than 1, so that can't be the case. So in this one, it should be, it would be the case if bigger. Right, so that would be the case if DNDS is bigger than 1. B, because a large proportion of mutation in non-synonymous sites are neutral. So in that case, the NDS would be equal, approximately 1. I mean, these are approximations in this case. C, because a smaller proportion of mutations in non-synonymous sites are beneficial when compared to mutation in synonymous sites. Let's keep that there. D, because a small proportion of mutation in non-synonymous sites are deleterious. So that's not the case. So a smaller proportion, if they are deleterious, that also wouldn't explain this. So that's not the case. A small proportion of mutation in non-synonymous sites are neutral. So that's not the case as well. So the small proportion of mutation in synonymous sites are beneficial. So they're mostly deleterious. That's why the proportions like this. So C is the correct answer to question 14. Any question thus far? I guess someone is typing. Why isn't it D? Ryan asks. So in D, it says that because a smaller proportion of mutations in non-synonymous sites are deleterious. So if they're so D would imply that the mutations in non-synonymous sites are mostly beneficial or neutral. So in both scenarios, so in the case of if most of the non-synonymous ones are neutral, DNDS should be close to 1. If most of them are beneficial, it should be bigger than 1. But in this case, it's smaller than 1, so it can't be the case. Right. So the only explanation when DNDS is smaller than 1 is that most non-synonymous substitutions are deleterious. And that's why the proportion is lower than 1. So, again, just to remind you, in the case of synonymous substitutions, because of the neutral theory or neutralism, the idea is that the changes in synonymous sites or synonymous substitutions, the rate at which they are going to arise is a fixed rate. It's like a ticking clock. It doesn't change because it does have no effect whatsoever. So it's neither beneficial nor deleterious. So that's why we are comparing the rate of non-synonymous to synonymous, since synonymous is just this fixed point of reference that we can use to see if most non-synonymous ones are beneficial, neutral, or deleterious. Hopefully I answered your question, Ryan. If not, please let me know. Okay, so apparently I have answered that question. So let's go to question 15. I think that would be the last one from this exam because you haven't you don't know about the quantitative genetics yet. So question 15, two loci A and B of the nematode C. remini have two neutral alleles each, A and B respectively. An experimental population was founded by 40% of, so these are diploid individuals, so if we were to look at the parents, so when they start, they have these haplotypes. So each individual carries, 40% of them carry these haplotypes, and the other 60% they carry, so they're diploid, so they carry two copies. In the case of the other 60%, they are only A and B. Okay, so that's the founding population. Experimental evolution, so they were allowed to mate and for 10 generations, and there is no recombination in this scenario. So no recombination whatsoever. So the linkage disequilibrium, or D, is 0 because of lack of recombination, really. right? So we know that when D is not 0, so when D is, I'm using the computer science language of the exclamation mark equal sign would mean that it's unequal to. So when D is not equal to 0, we know that so H prime for, let's say, AB would be H, the haplotype frequency of AB, minus the rate of heterozygosity, the recombination rate multiplied by linkage disequilibrium. So in this case, this is when D is 0, this part doesn't exist really, right? Because this is a R of 0 multiplied by D would be 0. So H prime AB would be HAB. So haplotype frequency is going to stay the same over time. So having said that, which one of these figures would be the correct answer? So which one is, given that there's no recombination, which one is the correct one? So since there is no recombination, again, okay, someone is answering. Figure A, right? So if there's no recombination, you're not going to have this crossover. So you're not going to have uppercase A, lowercase b, and lowercase a, uppercase b. These recombinants are not going to exist. So at the end, you're going to have the parental types. So the recombinants are generally referred to as non-parental types. So at the end of these generations, you're going to still have the same parental types because there was no recombination whatsoever. So any question thus far? If not, we can move on to the exam from 2000 and the answer. Jennifer asked what was the answer. The answer was A, because there's no way for the other genotypes to appear for capital A lowercase b and lowercase a capital B. So any other question? I think none of the questions from this exam are going to be, none of these are relevant to you, at least not for now. So there's no questions, so we can move on to the exams from 2014. Okay, where is that exam? Right. Okay. Okay, so this is the midterm exam, the second exam from fall 2014. We're going to try to answer as many of these questions as we can today. One, which of the following can cause heterozygotes to occur at a frequency lower than that expected under Hardy-Weinberg equilibrium? Founder effect, heterozygote disadvantage, population subdivision, small effective population size, all of the above. So which one do you think? So I know that population subdivision would result in that, right? That would be one. Heterozygote disadvantage would be another one, right? So all of the above, as Jennifer pointed out correctly. All right, so question 2. Consider the following experiment. You set up 20 populations of 10 individuals of the nematode C. elegans. Each individual is heterozygous at a marker locus with 2 alleles, plus and minus. The three genotypes at that locus show distinct patterns of locomotory behavior but have the same fitness. Every generation, new population. So again, these are neutral alleles. Then, what the sentence meant was when they said that they have the same fitness, even though the phenotypes are different, means that they're neutral. Every generation, new populations are founded from existing populations by sampling 10 individuals at random. So it's a Wright-Fisher model. How do you expect the frequency of plus minus heterozygotes to change over the first 20 generations? So how do you expect heterozygotes to change? Given the population size and the way they are evolving. Anyone? So there are A increases, B doesn't change, C decreases, D follows this trajectory of going up and then down, this parabola. So which one, in your view, is the correct one? McKinley says, wouldn't heterozygosity decrease? Yes, so that was the point of the question. The question, as you correctly pointed out, so when they say every time a next generation is created by sampling 10 individuals at random from previous generations, so they're simulating drift. And the population is pretty small, so you would expect, so since it's drift, actually it doesn't matter that the population is small because there's there are no, these different heterozygosity trajectories are very distinct. So again, to point out that this one means there's an increase, this one is a decrease, and this one is nothing, and this one just goes up and down, right? So the only one that is consistent with the drift is a decrease. I mean, the magnitude of this reduction of heterozygosity is going to be determined by this strength of drift, which is in turn determined by the population size. But in this case, it's pretty clear, since the other options are the ones that you wouldn't expect in a finite population. So C is the correct answer in this case. Sarah asks, so if the sampling population was larger, would we choose graph A? No, so graph A, because there's no way for, I mean, if the alleles are not neutral, so there's actual selection for heterozygotes. So if there's heterozygote, this heterozygote advantage, right? So if there's selection for heterozygotes, and then population is big as well, then A would be the case, right? So you need selection. So we would need selection for A. We need selection plus a large population for it to work, right? But in this case, the alleles are neutral. So even if you make the population big, heterozygosity is still going to increase. It's still going to decrease. Albeit at a slower pace than a smaller population. But in this case, we don't have a two trajectories showing a decline. There's only one. So a bigger population would simply dampen the effect of drift. It wouldn't reverse it. Okay, so evidently I have answered the question correctly. So now, consider the fitness function in the figure below. So we have, oh sorry, we have, what happened? Sorry for that. Consider following fitness functions. So there are three, four bar graphs with fitness and genotypes. Again, it's a two locus, two allele situation. The following figure shows change in the frequency of allele A over time under two of the fitness function in the previous figures. So this one is the change in P over time. To which of the fitness functions does the dashed line correspond? So the dashed line, as you can see, as a line that is that it starts at some point and goes down to 0. So which one would you expect to be? So we have to relate this dashed line, again, not the solid line, but the dashed line, to one of these fitness graphs. So first of all, from the examples you remember, you recall, do you remember which type of stability is that? So when the frequency just goes down, is it the dashed line, does it describe a stable system or unstable system? Anyone? So the dashed line, what type of system does it describe? A stable one or an unstable system? Anyone? Please. Unstable, yes, as Ryan and Sarah pointed out, it's unstable, right? So it presumably there is a equilibrium here, or higher than that. I mean, so this is the equilibrium, and since it was below the equilibrium, it went down. So that is, as far as we know, as far as you know, there's only one system that would have that. That is an under-dominant system, right? So which one of the figures A, B, C, and D show a fitness function that is under-dominant? As Ryan said, it's D. So D is showing this pattern, right? Where heterozygotes are worse off than both homozygotes, and that corresponds to an unstable system. So if we were to draw the rest of the alternative trajectory in the change in P, so if P is higher than equilibrium, value is going to go up to fixation, right? And D perfectly captures this system. So the correct one was D. Okay, so D is the correct answer. Let's move on to the next one. Question 4. Following figure shows the change in the frequency of the capital A allele from one generation to the next as a function of the frequency of the allele in the current generation. So it's delta P versus P under 2 of the fitness functions shown in the previous question. Which of the fitness function corresponds to a dashed line? So in the dashed line, P changes as the what is the word I'm looking for? So the change in P at the beginning is pretty high, and then it becomes a slightly slower. So which one in the previous figure corresponds to the dashed line here? So just remember this part. So remember this. Now we're going to go back to here. So which A, B, C, or D shows that pattern? Is it, which one is that? So in the case of B, when it's dominant, how is it going to look like? Anyone? So any suggestion if actually, if I find the okay. So no suggestions. So first of all, we want to see that what is the dashed line? Is it dominant, recessive, or codominant? So the dashed line P versus delta P. So it spreads pretty quickly. Actually, or actually it spreads slowly and then picks up. As McKinley pointed out, is recessive. So this one is recessive, while the other one is dominant. So as you remember, in the case of dominant, at the beginning it's pretty easy for it to increase in frequency because it's a dominant allele. But later, when evolution tries to distinguish between heterozygotes and homozygotes, it can't because both of them have the same phenotype. So then it tapers off. In the case of recessive, at the beginning the frequency is pretty low, so it slowly builds up. But then once the frequency is high, selection easily picks up the recessive allele. So in the previous one, we have to find a recessive, and which one is recessive? A, B, or C. So which one? And so in this case, is this one recessive? This B or C? So which of these fitness functions correspond to a recessive mode of selection? A, B, and C. We already know that D is under dominance. Okay, A. What type of selection does A represent? So this fitness function A. What type of selection is it representing? Over dominance, as Ryan has rightfully pointed out. So what about B? What type of selection do we see in B? Is it okay? So is it under dominance, over dominance, dominant, or recessive? So in the case of B, heterozygote and homozygote, both of them show the same have the same fitness value. So it should be dominant, right? Because capital A is dominant. A is dominant, right? So what about C? Is it dominant or recessive? C is recessive. So the one that corresponds to a dashed line is C. All right, any question thus far? Let's move on to under which of the, so question 5, under which of the following do you expect genetic variation to be maintained? Heterozygote disadvantage, negative frequency dependent selection, positive frequency dependent selection, selfing, all of the above. So genetic variation is heterozygosity, at least as far as we are concerned. So we can just say heterozygosity or H in its place. So heterozygote disadvantage would decrease heterozygosity, not increase it. Selfing would also decrease heterozygosity. As you remember, in case of selfing, heterozygotes, when they reproduce, half of their offspring are homozygotes, and so they're not going to mate with heterozygotes. So the frequency of heterozygotes just is halves every time at every generation, so it's divided by 2 over and over again at every generation. So that also decreases heterozygosity. So by that, all of the above is also not the case. So it's between negative frequency dependence or positive frequency dependence. So which one would maintain heterozygosity? Negative frequency dependent or positive? So positive frequency dependence, of course, is as the frequency of an allele increases, the fitness increases accordingly. Negative frequency dependent means that when an allele has a low frequency, it does have high fitness value. When it becomes prevalent in the population, its fitness value declines accordingly. So which one, in your view, would maintain genetic variation? Anyone? So negative frequency dependent or positive frequency dependent? Let's just to help you, so it's fitness and the frequency of, let's say, the allele A. The frequency is from 0 to 1, and the fitness is also 0 to 1. Positive is like this, and negative and just decline. So negative is the green one, positive is the red one. So which one would maintain heterozygosity? So positive or negative? Again, as you look at these trajectories here, which one would maintain heterozygosity? Anyone? No one really? Like, so does positive frequency dependent selection result in a maintenance of heterozygosity or not? So in the case of allele A, as it increases in frequency, its fitness value also increases, right? So as you move across this line, you just get better and better, and you are going to be selected for more strongly. So does that result in more heterozygotes or fewer heterozygotes? Feel free to just type. Doesn't matter if it's incorrect. So Sarah's Sarah, you mean more heterozygotes? So in the okay, so in the case of positive frequency dependence, right? When one allele becomes more gets a higher fitness value, selection is going to select for that allele. So there is no reason for selection to select for the other allele, which in this case would be lowercase a, right? So while the number of AA, so in this case, let's say all of them are diploid, AA is going to increase. Why? There is no reason for selection to select for heterozygotes, right? So AA, the capital A is going to increase, and capital A, lowercase a is going to decrease, right? So in the positive, heterozygotes are going to decrease. In the negative, though, heterozygotes are not going to decrease, because as one allele becomes more prevalent, its fitness advantage. Oh, the video is frozen. Does anyone else have problem with the video? Okay, so it's apparently it's fine for the rest. Well, the slides are a little bit funky, but hopefully you see the questions. My apologies for the audio visual lag. My internet is pretty high speed. I downloaded 100 gigabytes not half an hour ago in 10 minutes. So the internet is not is pretty good, but this platform seems a little bit shaky at some point. But just the point I want to make was that when it's positive frequency dependence, an allele is going to just keep increasing in frequency. So it's going to the homozygotes carrying that allele are going to increase in frequency. But in the case of negative one, negative frequency dependence is going to maintain heterozygosity. So it should be B. All right, so I think that's all for today. If you have any questions, just feel free to ask right now. This is going to hopefully be up. Oh, Jennifer asked why wouldn't so negative frequency dependence doesn't decrease heterozygosity because, so in this case, right? So you're okay, so let's say you are here, right? So you have very low frequency. Your fitness is as high as it gets. But as your frequency increases, your fitness value just goes down, right? So then selection is going to become weaker in favor of you. So the alternative allele is going to be selected for as well. And as you become very prevalent in the population, your fitness becomes very low. So selection favors the other allele. So then your frequency is going to go back to where it again becomes advantageous for you to be selected for. So then there's this push and pull, as when you are pretty low in frequency, selection is in favor of you, but as you become more as you increase in number, selection becomes against you, right? So then you can't increase, the population can't be just made of you as a single genotype, because selection is going to favor the other genotype as you become more frequent. So hopefully that answered the question of why negative frequency dependent selection would result in maintenance of heterozygotes in the population. If I haven't answered the question properly, please tell me. All right, so I think we're going to cover the rest of these questions and the exam on